So we have 4 pi r squared sigma t 1 to the 4th power minus 4 pi r squared sigma t 2 to the 4th power. So be sure to fix your notes. I left that sigma out and I stuck it in the end there, but I put it in its, shall I call it, proper location there. So there we have a relationship for the flux. But of course, that has to equal the power. The net outward flux in this region, the net outward flux must equal 120 watts or you will not be in equilibrium. All right. Also, the power out at the outer shell. So if we're looking at the power coming out of the outer shell like that, the outward flux of energy, F out, is going to be, of course, 4 pi r squared sigma t2 to the 4th, and that also has to equal the power, doesn't it? Because the net outflux from this surface is only from this surface, unlike the part in the middle. The part in the middle has energy coming from 2 directions, and the net outflow in the middle must be 120 watts. But when we get outside of the outer shell, there's only an outflow of energy. There's nothing sending energy in. So that makes it easy to get T2, doesn't it? T2 is going to be what? Well, I just simply move this to that side and take the 4th root of everything. So we have, it equals the power over 4 pi r squared sigma, and take the 1/4 root like that. Okay.
Professor?
Yes?
Did you say anything?
Start back at the beginning when we were talking about
Just right when you added the P to the power.
right when I added this power or that one? That one there? Okay, now this right here, we're describing the region between the 2 spheres. And so I'm saying 2 things. First off, the radiation between the 2 spheres is coming in 2 directions. Okay? That's these 2 terms. But I also said that the net loss of radiation must equal the power, or you will not be in equilibrium. So 120 watts being produced inside, you have to have a net outflow of 120 watts. But there's this plus that to get the net. Is that what you were asking? Go ahead.
If you look at the equation, you got the power equals the outflow of the first one minus the second one, but then right under it, you've got power equals the second one. How does that work?
It works just fine, thank you. How does that work? It works just fine, thank you. So, what you're kind of thinking is there's got to be twice as much coming out as going in.
Oh, yeah, okay.
Okay?
Yeah.
Good, that's enough. I didn't have to explain it. Good. Does that make sense to everybody else? His question was a good one. And my half an answer, was that adequate for everybody? Because I only gave half an answer on that. Okay, good. We're just about ready. Can I put numbers in? I think I did. Let's put numbers in there and calculate. Why don't you do that right now? Get the temperature, the temperature of the, get T2. I'll write it on the board quietly. I'm not going to say anything. Don't look up until you think you have it right. So you got that down, get the number, get everything else squared away, and calculate T2, please. When you're done, check it out compared to my numbers. Stefan Boltzmann constant watts per meter squared kelvins to the fourth. Now is a really good time to check the units. So watts with watts, meters with meters, and 1/1 kelvins to the fourth, take the fourth root. Yes?
The radius of the second jump is 4 meters.
No. See, the diameter is 4 meters.
Oh, man.
Did you get 80.55? Did I stroke my calculator correctly last night? Good. We all agree on that number. Great. All right, now I'm actually going to get around to answering his question much more specifically. Now we say from above, meaning this equation right here. Notice that what we just claimed, just like you noticed, that this term right here is also power. So we could write 4 pi r squared sigma t1 to the fourth minus power equals power. So 4 pi r squared sigma t1 to the fourth equals 2 times the power. There's your question right there. So please calculate t1. I'll ask you to go from here, calculate t1. I'll do the same thing. I'm going to calculate it quietly on the board. So please calculate t1. Did you get 135.5 kelvins for the temperature of the inner sphere? Obviously, the inner sphere has to be hotter because it's smaller and it's got radiation coming from 2 directions. So it's going to have to be hotter. By the way, just to show you something, if you very carefully demonstrate the units here, you put the units in here and they're exactly the same as you did before. You don't have to demonstrate them again. Just say units as above. Once you have shown that they are identical units, why do it again? Okay. So then the next thing, of course, engineers do is, I have a system, I'm releasing 120 watts inside, there are a couple of containers outside. Are the containers tough enough to withstand the necessary temperatures? You calculate the temperatures and say metal spheres, 80 and 135 kelvins, sure, no sweat at all. So it's an easy thing then to estimate what the constant operational temperature will be of a system. Now, as we think about the movement of thermal energy, remember there are 3 different ways of moving energy around. They are, of course, conduction, convection, and radiation. We've concentrated in radiation. It's important for us to realize that there's 2 different, I won't say ways, I'm going to say this. I know, outcomes. There's 2 different outcomes when you move energy. And let me explain the one that I'm particularly interested in. To do that, we're going to go back to a gas trapped in a cylinder. Here's a cylinder like this. And then I'm going to be very pinky here, and I'm going to draw an outer wall to the cylinder. And generally in my sketches, when I shade the outer wall like this, I'm saying we're making this of a perfect insulating material. A material that does not allow heat to transfer no matter what. This material is hard to come by. You can buy it in physics labs only. We will make a piston of the same material. It fits perfectly. There is no friction and there's no gas loss like this. So now we have a trapped gas. And we're going to push down on the piston. So the piston is going to end up at a new lower level like this. After we've pushed it down that amount. So, of course, we've done work in this system. We've done work. And where did that work go? Internal energy only, huh? You compressed it, you increased the internal energy. Delta U. Delta U equals the work. And of course, we can get the energy back out again, can't we? If we raise the piston back to the original position, then the higher pressure and temperature pushes the piston up. It does work back on the piston. So we can put work into the system, we can put energy into the system, and then we can get it back out again. That is a reversible process. As opposed to, imagine that I compress this, I put the work in, and then I so quickly remove the pressure that I essentially, you've got the piston down here, and of course the pressure is a result of molecular bombardment. Now I move the piston so fast, faster than the molecules are moving. So as I do that, I create a vacuum, and the gas then re-expands to fill that spot. In that case, the gas did not do any work, so you don't get the energy back again. Yes?
So, say that the insulation wasn't perfect, and if you had lost some thermal energy, if you moved it back up above the initial position, would it suck in a bit of thermal energy? And
Suck in. I'll buy that.
Well, it would be.
I'll buy that. Your scenario is we start with a not perfect insulator, but we are at thermal equilibrium when we start. Compress it, you heat it, and some of the energy is lost. Expand it, and yes, when you first expand it, this temperature will go below its original equilibrium temperature, and the energy would be absorbed again.